Okay, Windows 11 install has interrupted our class. But I'll post a video wherever that one happened to get cut off. So we're going to look at something here that's at a little bit more advanced because it uses a lot of stuff that we use in the course, but it's useful for review. Okay, so you can see that I've got a bunch of points here. Can you see them? It may be a little hard to see. They would show up well, I think, on the screen. And those points just happen to lie along a straight line, pretty much. They seem to lie along a straight line. Okay, so I went ahead and drew a straight line that stayed as close as possible on the average to the points. Really supposed to stay as close as possible to the average of the squared distance between the line and the points. That's a mouthful, and people can't visualize that very well anyway. I can visualize it a little bit, actually fairly well, but it's not really that important. We get a pretty good approximation here. Now, if this data shows, let's say, we're rolling a bowling ball down an incline, and the speed of that bowling ball is going to increase linearly with time. If it speeds up by 4 feet per second in 2 seconds, it's always going to speed up by 4 feet per second in 2 seconds, so long as it's on that incline. And as long as the incline's uniform and everything is ideal. That, of course, that's the ideal case. But if we try to observe it, well, say we got a stopwatch, we're trying to see where it is at each time. We're going to make errors with the stopwatch. We're going to make errors in locating the darn thing. I think it was here, but maybe it was here, maybe it was here. You know, there's at least a few inches of uncertainty in where it was, which is why the data points, if this is its position measured along the incline, and this is time, these data points will be somewhat scattered about the reality. The reality is that there's some straight line that almost perfectly matches what that bowling ball is doing, okay? So we're trying to find that straight line, so we take all the data. Now the data is pretty tight. It's in a thin band, about like this. So this line is a very plausible model for what that bowling ball is really doing. Make sense? So maybe we want to find the equation of that straight line. Well, it's easy to find the equation of that straight line if we've got a scale. Now, when I first drew this, I didn't have a scale. I didn't say X is 40 here and Y is 90 here. Okay. I just arbitrarily drew a vertical line away from the Y-axis and called it X equals 40. Could have called it anything. Okay. Oh, just positive. And I drew a horizontal line up here and called it Y equals 100. Nice round number. Okay. Number I wanted to use. This probably is a good model for a bowling ball if you adjust the incline just to the right level and measure its position in meters and its time in seconds. Okay. Well, to get the equation of the line, there's a number of things we could do. Basically, we want to take 2 points in the line. If we got 2 points in the line, we can do what I call a fundamental triangle and get a slope. Okay, so we do a fundamental triangle between this point and this point. We go up to here, over to here, back to here. There's a triangle. We label the rise equals this and the run equals that. The whole thing we learned to do early in the semester, and that you're going to be expected to be able to do on the exam because I want you to have that picture. Very important picture, especially when you get into calculus. But important enough even at the level of this course. I could have done that. Could have found the slope. And then I could pick one of these points and use that point with the slope. There's a point slope form for the equation of a straight line. Or you just use common sense with the slope and figure out what the equation is. That's what we did back in chapter 2. So you're going to want to be able to do that when you get to the final. Okay, the way I chose to do this, because it's more consistent with what we're doing now with simultaneous equations and matrices. We did this back in chapter 2. And everybody's done the assignment on 2 equations and 2 unknowns. And we've just talked about 3 equations and 3 unknowns. But for the first graph, which is this one, we assume y equals mx plus b. That's a general equation of a straight line. There are other forms of that equation. They would work just as well. The y equals mx plus b is pretty convenient. We take x equals 40 and y equals 90, so that x becomes 40 and y becomes 90, and we get the equation 90 equals m times 40 plus b. Then we take x equals negative 30, y equals negative 75. X becomes negative 30, y becomes negative 75. Now we have 2 simultaneous equations and 2 unknowns that we can solve for m and b. We can do that by elimination. We can do that by an augmented matrix. Now, somewhere up here, I've done that. Yeah, there it is. So here it is. First of all, these are the equations I just wrote down. Okay, I just took 2 points in that graph, plugged in x and y. I've got 2 equations, 2 unknowns. I switched the sides because it looks better if you have your variables on this side. Variables are m and b. Instead of x and y, it's m and b. And that's no big deal. We solve for m and b. Okay? And I think I solved this correctly. Now, I got into working with the fractions because it's important to be able to work with fractions. It would have been easier if I'd used decimal equivalent because all decimal equivalents are exact. And they're easier for people to work with. But why do things the easy way when you can do fractions? Because people are deficient in fractions. People need to think about fractions. The process is very simple. It's the process that we saw earlier in class. We've only got 2 equations and 2 unknowns. We can write those equations as an augmented matrix. 40m plus b equals 90 becomes 41, 90. Negative 30m plus b, that's 30m. Negative 30m plus 1b equals negative 75 becomes negative 31, negative 75. Okay? And then we just divide the first equation by 40, which gives us a 1 here. We know that we want a 1 here. There's no advantage in switching the equations and dividing this by negative 30. Okay? So we just get a 1 here. 1 divided by 40, 90 divided by 40. Okay? That's the only change we made. Equation 1 becomes the old equation 1 divided by 40. Equation 2 is still what it was, but we're going to mess with it now. Okay? So for equation 2, in the next step, we keep equation 1 the way it is. We got the 1 where we want it. We do equation 2 plus 30 times equation 1. If we look at the old equation 1 and equation 2, we see if we multiply the number in the first column of the first row by 30, we're going to get 30 because that number is 1. And if we add that to the number just below it, the negative 30, so we've eliminated x's. But we haven't had to write down any x's. We're going to get 0. So we multiply 1 by 30, add negative 30, we get 0. Now you go to the second column. In the first row, we have 1/40th. Multiply 1/40th by 30, we get 30/40, which is just 3/4. And we add that to the one in the same column of the second row, and we get 1 plus 3/4, which is 7/4. I didn't write out all the details of the fractions. It would be worth your time to work through them. Ask questions if you have them. But you don't have time, get caught up with other stuff. Okay. Then we divide, then we multiply the 90/40ths by 30. Okay. Well, first of all, 90/40ths is the same as 9/4. A little easier to multiply 9/4 than it is 9/40ths. 30 times 9 is 270. 270 over 4 is 67.5. And we add that to -75, we get -7.5, which is -15/2. Okay, that's not difficult. Just write it out. Numbers come up pretty easily, even with the fractions. Okay, now we come over here. We look at our third augmented matrix. We got a 1 at the upper left. We got a 0 below that. Then in the lower right of the 2x2 matrix, to the left of our dotted line, we have 7/4. We want 1 there. Because we've got 1 there, that tells us what B equals, right? And to get 1, we just multiply 7/4 by 4/7. So we do 4/7 of the whole row. 4/7 of 7/4 is 1. 4/7 of -15/2 is -30 over 7. Okay, -30 over 7. Okay, and that's an easy multiplication. Okay, so now we know what Z is. And we could write out our equations and plug in Z equals -37 and solve the first equation for X. Instead, I go one step further. I mean, we've got this is upper triangular form. It's perfectly usable. But there's another step I can take. I can get a 0 here. If I multiply the 1 in the second column of the second row by -1/40th, I get -1/40th, which I can add to this 1/40th to give me 0. Okay. If I do that, I've also got to multiply the -37th by 1/40th and add it to the 9/4. It's in the last, third column of my first row. Okay, when I do that, if I did the arithmetic right, and I actually kind of did this, 1/40th of -30 over 7, it's like -30 over 40, which is -3/4. And then that's times 1/7, which gives you 3/28. Okay. I think I might have made a mistake there. Because it isn't a -4/7, it's a 4/7. It should be 9/4 minus 3 over 28, which would be 63 minus 3 over 28, which would be 60 over 28. And that reduces down to 15 over 7, which is about 2.1. That's interesting. Okay. So I was a little bit off there. So this should be actually 60 over 28, which reduces down to 15 over 7. And just a little over, it's like 2.14. Okay. And the 4 is really irrelevant because remember that we just drew a straight line that looked like it fit those points. If we'd have drawn it just a little differently, it could have had a slope of 2.2, slope of 1.9 even. Okay. So there's no point in putting a 4 on that because it's not significant. 2.1 is kind of close, plus or minus maybe 10% of the slope of that line. Okay. So does that kind of make sense? Steps that you're used to, I think. You've done augmented matrices with the 2 by 2 helps. Okay, you look a little doubtful. Anyhow, they're in there. So if you haven't seen them, you will. Well, what's that tell us? That tells us that the formula for this line should be y approximately equals 2.1x. And okay, it was 7/4 37 minus 37, which is about 4.3. Okay. That's a model from the 2 points that we estimated. Does minus 4.3 seem to fit for the y-intercept? Because if x equals 0, you're going to get y equals negative 4.3. Well, right here is the y-intercept. Could that be y equals negative 4.3? Well, no. If this is 75 here, this is probably more like 7, maybe even negative 10 instead of negative 4.3. Still, on the scale of the graph, negative 10 isn't going to be that much below what we are, so it's pretty close. If we do a slope, now if this went through the origin over to the point 40, 90, we'd have a rise of 90 and a run of 40, which would be 2.25. That would be our slope instead of 2.1. Actually, the slope would be a little steeper than that because the run doesn't go all the way from the origin out to x equals 40. It goes from maybe x equals 5 to x equals 40 or something like that. So it'd be a little over 2.25, maybe 2.4 or 2.5. So 2.1 might not be completely representative. But remember, this is a hand sketch graph, and I estimated these coordinates by eyeball, and I wasn't all that careful about the estimates. I used round numbers, or could have used some refinement. Of course, I probably would have made it worse if I did. But still, you see that this scatter graph gives us a pretty good model. And if our data is pretty accurate, that model might give us good information about how fast that bowling ball is moving at what time. If we put this data into Excel, know how to use Excel? Well, have you ever done a trend line? Okay. Well, it's easy. I mean, you can learn it in 5 minutes. You put your points in, coordinates in one column, the x coordinates in one column, y coordinates in another column, and you click on something that makes a scatter graph. What are the options? I don't know where to find it. You ever done that? Okay. Yeah, well, you just put stuff into column. You've done that, right? And just click on scatter graph, and it'll give you a graph. And then you click on, right click on the data points and ask it to add a trend line. Click on linear. Click on show the equation on the chart. And it'll give you the equation that is the best fit to your data. Okay? Which is a lot more accurate than hand drawing it. But if you hand draw it, you have better insight into what's going on. So eventually you'll learn to do that in Excel, take a statistics course or whatever, or in some other software. Okay. Now, the other two graphs that you can kind of see where the data points are. They kind of follow the pattern of this curve. First, I drew the data points, then I drew the curve. Then I decided to put a scale on it, put x equals 10 out here, y equals 100 here, and estimated the coordinates of this point and this point. Okay. Then I estimated, this thing might be exponential. It might be leveling off at an asymptote a little bit above the x-axis. So I said, maybe the asymptote's at y equals 3. I'm not going to use that right now. I'm just going to assume that this kind of looks like an exponential shape, doesn't it? Well, if it's an exponential shape, then for the second graph, this is the second graph, we're going to assume y equals ab to the x. Or we could use y equals ae to the kx. We can solve that system of equations. And if you're a little behind, you might not have got completely into that, but I think you've done something. Actually, that's one of the sections I think you're still behind. Okay. So this will give you a little bit of a heads up. If we got the model y equals ab to the x, then point 10, 100 says x is 10, y is 100. Well, if x is 10, we have b to the x, we have b to the 10th. If y is 100, well, y is 100. And then we have negative 620. X is negative 6, b to the x would be b to the negative 6. Y equals 20, so y equals 20. And there's a system of two equations that we can solve for a and b. And it's kind of nice with this form that we don't have to use logs and stuff as we do for one of these models. So it's two equations. I say the easiest way to solve it is divide left side by left side, divide the right side by the right side. If you divide the right side by the right side, the a goes away, and you just end with b to the fourth equals 5. Okay, which is an easy equation to solve if you remember the laws of exponents. You do the 4 to the 1/4 equals 5 to the 1/4, and there's your value of b. Okay, so I haven't solved that yet. I'm going to do that on the MDE video. Okay, then real quickly, you got this one. We don't know what that is. This is fairly obviously exponential, although you've got to check it out and see if it works. This looks like it might be a power function, like it might be the right-hand side of a parabola. You have the y equals x squared function. Or it might be some other power of x. Okay? Or it might be exponential. So we do all the same stuff. We get 2 points on this graph, and we take two possible models. Is it exponential, y equals ab to the x, or is it a power function, y equals a x to the p? Okay. Well, we can write the equations we get if it's ab to the x, and we can write the equations we get if it's ax to the p. Okay, we can put our 2 points in either of those forms. We get simultaneous equations, and then we attempt to solve them. Okay, and I'll be going over those solutions, and I'll kind of post that both for this class and for the other class. Well, it looks like Zoom stayed with me despite the update from Windows 10 to Windows 11. We'll see what it did to my other video and repair it somehow.